Hello everyone. Continuing on from where we left off in our last video, we were talking about sample versus population. So just as a recap, a population is the entire group of interest. So this would be something like if we're looking at all USF students, and that's who I'm interested in say something about. A sample is a subgroup of that population that we want to be representative to then try to say something about our population. So this example, we want to determine whether each number describes a population parameter or a sample statistic. And what is our reasoning? So, 1. In the United States, a survey of 9,400 individuals aged 15 and over found that such individuals spend an average of 5.19 hours per day engaged in leisure and sports activities. Okay, so in this case, these 9,400 people, because it has the word survey, which again, as a reminder, means that we are getting a sample, is sample data, meaning that it is representative, hopefully, of some bigger group. This would maybe be all people in the United States, 15 and over. So in this case, because it's specifically sample data, this means that this would be a statistic. Okay, question B. The freshman class at a university has an average SAT math score of 514. So in this case, because it does not tell us some specific group of interest, I'm assuming in this case that the freshman class is our group of interest. So this would probably be a population, meaning that these SAT scores represent a population parameter. They are describing the population, which in this case is your freshman. Okay, part C. In a random check of several hundred retail stores, the Food and Drug Administration found that 34% of the stores were not storing fish at the proper temperature. So in this case, it's a random check of several hundred retail stores, but it's specifically not saying that it is all retail stores, meaning that this is in fact sample data, so this is a statistic. Okay, part D. In January 2021, 54% of governors in the 50 states of the United States were Republicans. So the fact is that there are 50 states that make up the United States. This means that this is in fact population data. It is accounting for every governor for each state that makes up the United States, meaning it is population data. So this value that is saying something about those governors that represent the states means that it is a parameter because it's describing something about the population. Okay, so for the 2010 census, the Census Bureau sent short forms to every household. Short forms ask all members of every household such things as your gender, age, race, and ethnicity. Previously, a long form, which covered additional topics, was sent to about 17% of the population. So for the first time since 1940, the long form was replaced by the American Community Survey, which surveys more than 3.5 million households a year throughout the decade. These households form a sample. In the course, you'll learn how to use data collected from the sample to then infer some characteristics about the entire population. Now, why is this example important? Well, because as I mentioned before, every 10 years, the United States has to do a census, meaning it has to specifically go out and get certain information about everyone in the U.S. Now, mind you, some people will always be missed, so it's never truly everyone, but everyone that is possible to get. But you'll notice in this, we also talked about the fact that there was also the long form sent out to a subset of that population, meaning we are getting sample data, which we're getting more information about, which we then might be able to infer about the rest of the population. So in these two graphs, I also wanted to show you how sometimes you can say something in statistics that is completely accurate and still can give a different message depending on what you're showing. And we talked about this when you're presenting your data. So if you look at the bar charts on the left, the first one is the fastest growing states by population change. And you'll notice we have things like, for example, like Texas is the 5th highest growing state according to this data. Now, if you look at the bar chart below this, you will see that it is the change in state populations by the actual number of people who move, meaning the biggest absolute difference of change. So not the percentage of change, but the amount of people that came into the state. And you'll notice in this one, suddenly Texas is the highest population growing state. So now why might this matter? Well, this might be because if I'm trying to show that people are interested in moving to my state, I may want to show the percentage growth if I'm a smaller state like Arizona or North or South Dakota, something like that, where I could show, well, look, our population went up by 2.4%. Yeah, it's only 20,000 people, but it went up by a big percent. Whereas in Texas, on the other hand, for it to move that same amount because the population is so much larger, it would be a lot more people. So what they might say, instead of saying, okay, well, we only went up 0.7%, they might say, okay, but we grew by 200,000 people, meaning we grew 10 times more people than they did that came into our state. Now, as a percentage, not as big. And you might want to use either of these descriptions to describe the change in population for your state. Both of those numbers are completely accurate, but they give a very different meaning to what you're showing. Again, this is where you want to sometimes present data that will make a case for whatever you're interested in. Now, the reason I kind of bring this up is you see this a lot, and this is one of those takeaways I'd like you to have from this class, is you will see whenever people are describing something, they'll say things like this. They'll say, well, we cut $680 million from our budget. And you're like, oh, that's a huge number. And then someone else will come and say, okay, you've only cut 0.2%. So one of them is saying, look how big this is. And the other would say, look how small of a change you've actually made is. And this is one of those things whenever there's arguments about things like cutting or expanding NASA's budget. NASA's budget is only a fraction of a percent of the entire United States budget. So it sounds, if you want to sound like, look at all this money we're wasting, you might say, well, we spent $100 million doing this project, which was a failure. Whereas in somebody else might say, it was such a minuscule percentage that it is not important for us to cut that when there are bigger things for us to deal with. And this is, again, where this kind of stuff can be vitally important. And it's really important that you understand this. Okay, so now let's talk a little bit more in depth about some of those terms that I've used so far in the class. So descriptive statistics is the branch of statistics that involves the organization, summarization, and display of data. So this is the collection, presentation, and description of our sample data. So to put it in other words, it's describing the data you actually gathered. So if I have a population, I'm going to use USF students, and I grab 300 students. Descriptive statistics would say something about that. What is their average age? What's the average GPA? What's the highest GPA? What's the tallest person? Who's the shortest person? What's the average height? These are all things that describe the data that I actually have, those 300 students. So numeric values or graphs calculated from the data set with the purpose of characterizing the behavior of those variables, meaning that we are specifically talking about that sample data. Inferential statistics is the branch of statistics that involves using a sample to draw conclusions about a population. So a basic tool for a student of inferential statistics is probability. So what we're doing a lot of times is we're then trying to say, okay, my sample, my students, my 300 have an average GPA of, let's say, 3.4. Then I might want to infer that the population average, USF students in general, also has a GPA around 3.4. Right? So I could then try to infer something about the population at large. So making decisions and drawing conclusions about a population, right? So I might be able to use this data to then draw some conclusion about my population. So this involves methods of using information from a sample to draw conclusions regarding our population. We talked a little bit about this. This could be in the form of a point estimate. This was the GPA I got for my sample. This is the GPA I'm estimating for the population. It could be an interval estimate. I believe the GPA estimate, based on what I have, should be between these two values. It could be a hypothesis test. Well, based on the data that I have, I'm going to test whether this makes sense for this to be a GPA for the population. Things like that. These are all ways that you could then infer something about the population, and we will cover all of those in this course. So, describe example 1, descriptive and inferential statistics. Decide which part of the study represents the descriptive branch of statistics, what conclusions might be drawn from the study using inferential statistics. So in a recent survey, it was found that 58% of patients chose to use natural treatments for some specific condition. 71% of those that chose to use natural treatments were below the age of 35. So in this case, descriptive versus inferential. Well, in this case, we took a survey, which means we have some sample data. It's saying that 58% of the patients chose a natural treatment. That is describing the data that we took, that sample, meaning that this is descriptive statistics. Of that, it's saying that 71% of those that chose natural treatments were below the age of 35. So again, this is describing our sample, meaning that this is descriptive statistics. Now, what might I infer about this? I might infer that young people are more likely to choose natural treatments, meaning that if I were a pharmaceutical company, maybe when I'm advertising my different treatments, I would specifically focus on advertising to younger audience members for natural treatments because I want to try to sell my product to you. Okay. So descriptive statistics involve statements such as approximately 58% of patients chose natural treatments, or 71% of patients chose natural treatments are under the age of 35. A possible inference is that younger individuals are more likely to choose a natural treatment. So note, the major use of inferential statistics is to use information from a sample and infer something about our population, right? So just because we have this sample, we can say something about that sample. We then want to be able to say something about the population at large. Example 2. Of 75 randomly selected students at the university, 35 students were majoring in medicine. So in this case, because this is 75 randomly selected students at a university, this is a sample. So my descriptive statistic is that 35 of the 75 are medicine majors, or pre-med probably, meaning that what? About half the students study medicine. So in this case, I might infer that this school has a very strong medical program, and a lot of students here want to study medicine. Things like that. Example 3. Sarah did a survey of her college to identify how many students prefer to use college shuttles to reach campus. Of 212 randomly selected students, 163 said they used shuttles. Okay, so in this case, again, we have a sample. 212 students that we're hoping represent all of the student body. She found that 163 said that they used the shuttles, meaning that she might, so these are descriptive statistics. You might be able to make some ratio or something like that to describe how many students use shuttles as a whole. But you can then say, as an inference, we might say 77% of all college students will use shuttles to reach campus. Now, is it true? It might not be, right? That's why we need our sample to be representative, because maybe Sarah did her sampling near a bus stop and she happened to get a lot of students who were just arriving to school taking shuttles. Example 4. A study of 1,502 U.S. adults found that 18% of adults from households earning less than $30,000 annually do not use the internet. Okay, so in this case, this one wants to give us all the information about it. What is our population? What is our sample? What is the descriptive statistics from this? And what are some inferential statistics we might conclude from this? So in this case, our population, it says a study of 1,502 U.S. adults were found that 18% of adults from households earning less than $30,000 annually do not use the internet. So in this case, our population would probably be all households earning less than $30,000, probably in the US or whatever country we're looking at. Our sample specifically is those 1,502 people that make up those households that are earning less than $30,000 a year that we're looking at. Our descriptive statistic would be that 18% of those adults do not use the internet, meaning that looking at individuals, those 1,502 that have a household income of less than $30,000, 18% of them said they don't use the internet. That's a descriptive statistic. 18% do not use the internet. Or you could flip it and say, okay, well, 82% do use the internet. The inferential statistics might be about 18 to 20, 18% of people in general don't use the internet. Or rather, not in general. Of households making less than $30,000 a year, about 18% of people won't use the internet. Or it could be, again, 82% of people will use the internet. So remember, population is the group of interest. Sample is the group we're actually getting the data for. Descriptive statistic is saying something about the actual data. Inferential statistics is then trying to infer something about that population or group that we're actually interested in. Okay, next one. A study of 1,000 U.S. 401k retirement plan participants found that the percentage who do not know how many years their retirement savings might last is 32%. So in this case, our study of 1,000 U.S. 401k retirement plan participants, that's our sample, right? It's 1,000 people in the U.S. who have 401k retirement plans. Our population from that would probably be all people in the U.S. who have 401k retirement plans. Our descriptive statistic is that 32% don't know how many years their retirement will last. So we might infer about the population that around 32% of all 401k participants do not know how long their retirement will last. Okay, so now let's talk more definitions. Like I said, there's a lot of definitions in this section. So the first one is a variable. A variable is just a characteristic about each individual element of a population or a sample. So a variable would be something like height, weight, GPA. This is something that describes a particular aspect of either a population or a sample. So you can have a variable for either one, right? GPA for all USF students, that's your parameter, or GPA for a subset of your USF students. That would be my statistic. Data, which again, singular of this would be datum, is a value of the variable associated with one element of a population or sample. The value may be a number, a word, or a symbol. So remember what I told you before about data being specific outcomes that we have, right? It's counts, it's measurements, it's things like that. Well, a datum, a single data point, would be, for example, if we're looking at GPA, it might be if I have a sample of 300 USF students, a datum would be the GPA of a single student. The plural, the data, would be the GPAs of all the students in that sample, or some subset, something like that. So it is the outcome of a particular variable from a sample or a statistic. For a sample or a population. Now, one thing I want to point out in this, though, is that our data, it says, can be a number, a word, or a symbol, right? Because think about this. Data does not have to be numeric. For example, it could be placement in a race, first, second, and third place. While you might think, well, those are still numeric, they are, but they're not numbers that have any sort of numeric meaning other than, in this case, ordering, right? First, it did better than second place did better than third place, first did better than third place. But otherwise, they're not some sort of number that you can do anything with. You can't say, well, if I take first and second place, they make third place. That doesn't make any sense. So one thing you might see is that sometimes numbers can be used like letters, right? So for example, if I have a sports team or some sporting event, I could use numbers or letters to represent a player, right? If I'm watching football or NASCAR, if I see 42, that number does not have any meaning. It is a label. It is just a way of representing specific player 42 or specific car 42. Similarly, we could have the word, okay? So if somebody comes in, let's say that I'm filling out a survey at a hospital, and it asks, does the person have diabetes? Yes or no? Well, guess what? Now your data is a word, yes or no. It could also be a symbol, right? So just whenever we talk about data, most people think in terms of numerical data. It has to be a number. But your data could actually be any information about that variable. In fact, we have a whole field of statistics called categorical data analysis, which is dealing with what are called categorical data, which is to say this group or that group type stuff. And we'll talk more about that kind of stuff later. We don't really do categorical data analysis, but I'll talk a little bit about the actual topic. An experiment is just a planned activity whose results yield a set of data. Okay? Sampling error is the naturally occurring discrepancy between a sample statistic and the corresponding population parameter. Now, I actually want to briefly talk about this one because whenever we're looking at sampling error, this one is specifically, and I'm going to use general notation at first, which is the difference from some point estimate, which I'm going to do as theta hat, from our actual theta. And then we don't care about how far it is, so we're going to take the absolute value. This is oftentimes how we describe error. So if we look at mean, for example, this theta hat just represents a statistic. So this might be something like the mean of our sample minus this theta represents our population parameter. So this might be, for example, mu. And all it's saying is how far away is my sample statistic from that population parameter. So for example, if we had like a number line and my mu is right here and I have an x bar that's right here, it is just the distance between these two. It is how far off is my estimate, which I remember I'm using to try to say something about and trying to infer what this population parameter is. The distance between them, that is our sampling error. That is how much error we have from however we got our data, because we're using a sample to get this value. So whatever distance we have. Now the problem you might originally think when you see this is, well, I don't know what mu is. And that's actually a really good point, and that'll come up later in this course. Because if I had the population data to know what mu is, then why would I be using a sample to try to estimate what mu is? I would already have mu. So generally, this is more of an idea of what the error represents. The error represents how far off am I from this population parameter that exists. I don't know what it is though, but I do know that some amount of error does in fact exist. Okay, next we have individuals are the objects described by a set of data. This could be a person, animal, it could be a place, or a thing. In a medical trial, the people in a study are referred to as subjects. Now, one thing you'll also hear me sometimes say is I'll refer to things as elements. This is because in set theory, any individual outcome from a set of possible outcomes is called an element. And for example, when we do probability, I will be teaching you about this. So oftentimes you'll also hear me say element. Okay. Also in clinical trials, individuals are oftentimes referred to as subjects. Okay, so now let's do an example. The statistics department at USF is interested in learning about the average grade received by STA 2023 students in spring 2021. They considered 50 randomly selected students for this study. So in this case, the population would be the grades of all of the STA 2023 students from spring 2021. Our sample is any subset. So in this case, it would be something like if we took those 50 randomly selected students, that's our sample, those 50 randomly selected students. The variable, the thing that we're interested in actually measuring, is their grade. So the statistic would be the grade of those 50 students. The parameter that I'm trying to estimate would be the grade, or average grade probably, of the population, all of the students from STA 2023 from spring 2021. The data is the set of grades from STA 2023 students that I have. The parameter of interest is the average or population mean grade of all STA 2023 students, and the statistic is the average or sample mean grade for the group of 50 randomly selected STA 2023 students. Okay, more terminology. A valid measure is one that is relevant or appropriate as representative of that property. Otherwise, this measure is invalid. So I won't go too deep into this one, but basically, does this make sense as a measurement? Now, there could be a couple reasons why this may or may not be valid. For example, if I'm looking at the height of a random person, does it make sense to say somebody is 64 inches? Yeah, that's a pretty reasonable height. Does it make sense to say that someone is 1,326 inches? No, not here. That does not make sense for our data. That would probably be invalid. An example of this would come up when I'm entering grades in Canvas if I have a grade that's out of 100 and somebody somehow gets a grade of 666, Canvas will actually flag this and be like, that doesn't make any sense. So what happened? Well, I probably typoed. It was probably meant to be a 66, and I actually just triple tapped 6 instead of double tapping it. And it knows this because it doesn't make sense for the data that I have. So it's not a valid measure. This could also be something where it doesn't make any sense. Like, for example, if I roll a 6-sided die, my outcomes could be 1, 2, 3, 4, 5, or 6. So if somebody said the outcome was Jack, like they drew a card, that wouldn't be a valid measure. That doesn't make any sense based on what we're measuring, right? So it could be that somebody got mixed up and they wrote the wrong outcome for the wrong game in this slot, something like that. A reliable measure is a measurement such that the random error is small. So if you remember, the random error is how far we are off from the population value, meaning that if I were to think of this like a bullseye, a reliable measure would be ones that are close to that center value, which in this case represents my population parameter. Now, the thing is, you got to be careful about this is we don't really talk about this, but there's other ways you can talk about data. For example, in this case, we're looking just at the fact that the random error is small, but there's also some ways of looking at reliability where you're looking at how much does it change, right? So this might be referred to things as like sensitivity, things like that. But for example, I might have something like this where, yes, they're very far off from the actual value, but they're reliable in the sense that they are not moving consistently, right? So this one has a lot more variability to it. This one has a lot less variability, meaning that while this one might have a smaller random error, this one would have a lot more precision. So this would be a more precise measurement. This would be more reliable. Okay. Next, in a population data, the variable that is measured for every individual of interest, and this survey would be called a census. So if you were ever measuring everyone in a population, this is called a census or a population census. For sample data, if a variable is measured only for some of the individuals of interest, that means you're getting a sample, this is called a survey. So if I go and take a survey or a sample survey, this means, remember I mentioned earlier when I saw the word survey, I knew it was a sample, because if I say I did a survey, it means I went and gathered data from a sample. If I said I performed a census, this means that I went and gathered data for all individuals. Okay. So the last thing we're going to talk about for this video is qualitative versus quantitative variables. So qualitative or categorical variables are variables that categorize or describe an element of our population. This consists of attributes, labels, or non-numeric entries. Remember I mentioned the non-numeric entries, things like player 42. It is a variable that has nominal measurements that describe an individual by placing them in a category or a group. So nominal just means in name only, right? Are you on the blue team or are you on the yellow team? Are you in, the advanced team or are you in the remedial team? These are just ways of describing the group or the outcome or the variable of interest that you're looking at. So examples would be things like phone numbers, college year, meaning freshman, sophomore, junior, or senior, and addresses and colors, right? These are all ways that describe something, but they don't have any sort of numeric meaning. Even phone numbers, which are numbers, they're basically just labels. We could have just as easily have made them letters. We could have said your phone number is AKCBL1YL, right? That would work just as well, because all it is a specific label that describes which directory it goes to and things like that. Okay, so next when we come back, we'll look at qualitative measures. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.